Okay, good day. Introductory algebra at Simpson University. We are going in this video to discuss the real numbers. And while we discuss the real numbers, we're going to do 6 things today. The first thing we're going to do is we're going to define all the subsets of numbers that eventually make up the real numbers. Then we're going to talk about how to graph them on a number line. We're going to work with decimals as well. So we're going to review how to turn any number into a decimal. We're going to work on, given a number, can we classify it into the right set and subset? And then we'll also talk about order, which essentially is inequalities, less than and greater than. And then we'll talk about absolute value, and we'll probably discuss absolute value in a little more detail than you're probably used to. Okay? So there's our goals for what we're going to do today. Let's go through this video now. So the first thing we want to discuss are the sets of numbers that make up the set of real numbers. Now, as you know, as you went through elementary school, the first place you started with what was called the counting numbers. Okay? Counting numbers. And the counting numbers essentially started with the number 1, and then we would add 1 each time, 2, 3, 4, etc. Those are called the counting numbers. They actually have a more mathematical name, and that mathematical name is the natural numbers. Sometimes people call them the natural counting numbers. So that's a set. Then we added a very special number to that. That number that we added was the number 0. And so that increased the size of our set. And we gave it a new name. We called them the whole numbers. All right. And that set of numbers then became 0, 1, 2, 3, and so on forever. So that was the set of whole numbers. Now, these are just the typical numbers that we use, and it's from these that we can create everything else. So if you were like me, somewhere probably around 4th or 5th grade, then you were introduced to the integers. And so you started to talk about positive and the negative numbers. So you took into account the opposites of these. And so your set became different. -3, -2, -1, 0, 1, 2, 3. And as you can see, we are, and this is on and on in both directions, we are expanding our set of numbers and understandings. Once we develop the integers, then the very next thing we started to do, just real quick, why the integers? Why did we start to add the negatives? Well, at this point, if you think about elementary school, you were adding, subtracting, multiplying, and dividing. You were learning how to do that. So by 4th, 5th, 6th grade, when the integers are introduced, you can begin to ask the question, well, can you take a larger number from a smaller number? And so we started to look at things like that. And so 2 minus 3, we began to say, could that have a result? And this is exactly what happened historically with the Greeks and the early algebraists and so forth. They also wanted to understand, and so it became very easy to talk about a new type of number. And so they began to talk about the negative numbers. And you could find the location of those numbers, they would be on the other side of 0. So it's a very natural development in systems of numbers. So counting numbers, whole numbers, integers. And there's a whole set of properties that come about because of the integers. You can begin to talk about the opposite. So if I give you a number 2, the opposite of 2 is negative 2. Okay? And so, and then we give them another name besides opposite. We call them the additive inverse. Okay? And why do we call them the additive inverse? Because 2 plus a negative 2 is equal to 0. So we start to develop properties and with the operations add, subtract, multiply, and divide. And that's why integers become important. Well, of course, the same thing begins to happen when you introduce the next set of numbers, and that next set of numbers would be the rational numbers. Okay? And the rational numbers are what we commonly call the fractions. All right. And they came about because of the operation of division. Whereas integers came about through addition and subtraction, rational numbers came about because of division. Now, if we kept things in the whole number integer realm, where you might have 20 divided by 4 equals 5, and you always got whole number results, and when we first learned division, that's what we did. But then we started to make things more challenging, and we started to say, well, how many 7s go into 20? Right? And, in elementary school, you'd draw pictures and, you'd have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20. And then we'd go, okay, there's 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Oh, there are 2 7s that go into 20, but this is not the whole answer because we still have 6 left over, and we started to talk about remainders, and then eventually we started to say, hey, that's 2 6/7. Okay? So rational numbers, that whole idea of fractions begins to get developed from these ideas. Now, rational numbers are a ratio of 2 integers. All right? And let's see, ratio of 2 integers, A and B, as long as B is not equal to 0. Okay? Now, why do we say that? Well, when we make this sort of definition that this is a rational number, it's a ratio of 2 integers, A and B, as long as B is not equal to 0. Why do we do that? Well, what we're looking at is we're looking at things like 3/4, there's 2 integers, negative 2 7ths, there's 2 integers. These are rational numbers. 112 thirds, 2 rational numbers. These are all rational numbers. We could do 0 over 4. That's a rational number. But as soon as we make the denominator 0, so suppose we write 15 over 0, what we are saying is we're saying 15 divided by 0. Well, how many times does nothing go into something? Does it go an infinite number? Does it go only once? You have many, many answers. And based on our definition of division, which is the opposite of multiplication, if this was true, 15 over 0, then 15 divided by 0 would equal some number A. just some number. We don't know what it is. But then this would mean that 15 would equal 0 times a. And so do you remember writing these reverse mathematical sentences in maybe high school algebra or maybe even elementary school? Well, what do we know about anything times 0? It's always 0. So what this thing is saying is that 15 equals 0, which is false. Therefore, you can't divide by 0. Okay? Cannot divide by 0. And you have just seen an example or a proof of why not, why you can't do that. Okay? So, rational numbers. Ratio of two integers as long as the denominator is not equal to 0. Okay? Now, once you get that rational number, then one of the things we start to do is we write those rational numbers as decimals. Once we understand, oh, hey, 2 divided by 4 is the same thing as saying 2 divided by 4, and we start to write those as decimals. Okay, so that means 4 goes into 2 how many times, and we begin to do the division. All right, and so 2 divided by 4 is equal to 0.5, or if you wish, if we say it in correct decimal, 5/10. All right, because the place value is tenths. So that then becomes the decimal representation of 2/4. Okay. It turns out that for any fraction, only two things will happen. So if we did like, let's do a simple one, like 2/3. And so that's 2 divided by 3. So that would be 3 going into 2. And if we start to do that, that goes into 18. We have 2 left over, so it goes 6 times. Bring down the 0 and we get 18. It goes 6 times. And we go on and on and on, and the same pattern happens, and we get a repeating decimal. So it turns out, in fact, even on this previous problem, when we divided by 4, we just get 0, and then it goes in 0 times. And we subtract and get 0, and then it goes in 0 times. So even dividing 2 by 4 is a repeating decimal. It just repeats zeros versus repeating numbers. It turns out you can also say that rational numbers, all the fractions we're used to, rational numbers have a repeating decimal representation. That's pretty cool. All right, all rational numbers can do that. All right, and they'll all repeat. Either they'll repeat zeros, which is what we call terminating, or they'll repeat some sequence of numbers. Like 1/7 repeats 6 numbers, and then it repeats those same 6 numbers when you divide by 7. Okay? So, what happens then? Somebody begins to ask the question, and they say, wait a second, what if something has a decimal representation? Okay? But it never repeats. So in other words, now notice up here, this one repeated the zeros, and it would repeat zeros forever. So it goes forever. This one repeated sixes, so it goes forever. So a decimal representation that never repeats means it has an infinite decimal representation. It goes on forever and it never repeats. And if I asked you to think of a number based on your previous mathematical experience, you might come up with pi would be a good example. 3.141596. It goes on and on and on forever. All right. Another one you might be familiar with is the number e. If you had Algebra 2, you probably talked about the exponential, which is approximately 2.718 and goes on forever. And then others you've seen mostly in geometry, things like that aren't perfect square roots, like the square root of 2, square root of 3, square root of 5, the cube root of 7. There are all kinds. And then there's just decimals that you can write. 0.02002, nope, 0.002. They may have a pattern, but they don't repeat. You keep plopping in an extra zero. It turns out, if you have a decimal representation that never repeats, that is called an irrational number. Now, if you take all the rational numbers and you combine them with all the irrational numbers, those two things together create the real numbers. All right? And that is how you create the real number set. All right? And so our study in arithmetic in elementary school through the mathematics of high school is really about studying the set of real numbers and the properties you can use to understand them. Okay, next thing. So this is a pretty quick portion right here. Next thing is that you want to be able to graph all these types of numbers on a number line. Now, you've probably seen this before, but I want to remind you. If I'm drawing a number line, I'm just going to put 0. And then I make a distance, and I call that distance 1. And then essentially what I do is I copy that. And then that lists all the positive integers for me to the right. And then if I copy it to the left, I am listing negative integers, or the negative numbers. And then anything else can be placed in approximately the correct place if you know its decimal representation. So for instance, if I have the square root of 2 and I can find it on a calculator quite easily, it's 1.414. Now it goes on forever. But even though it's irrational, I can place the square root of 2 approximately where it goes on the number line, between 1 and 2, just a little closer to 1 than it is to 2. And you can do that with any number. Suppose I had 7/4. Well, if I can write that decimal representation, that's 1.75. And so that's actually a little bit closer to 2, but then that's where 7/4 will be. Okay? And that's my process of putting things on a number line. And so you want to be able to do that. We'll solve some inequalities and things like that. we want to be able to put things in the correct place. Okay, next thing. So one of the typical problems you get is you want to classify numbers. So suppose somebody gives me a list of numbers and they could give it in a set or whatever. So something like -9, -1.3, 0, 0.3, square root of 9, and square root of 10. All right? And I want to list which ones go in each set. So for, in other words, which ones are a natural number, which ones are a whole number, which ones are an integer, which ones are rational, and which ones are irrational. They're all real, so I would list all of them. Now, the natural numbers are only those that are a counting number, 1, 2, 3, 4, 5. So, in other words, I see this -9, it's negative, it's not natural. 1.3, 0 is a whole number, 0.3. Square root of 9, square root of 9 is equal to 3. That's actually a natural number. So I would put the square root of 9 right there. So the whole numbers, since square root of 9 is natural, it's also a whole number, but so is 0. 0 is a whole number. And then you just proceed through. Integers then will be negative whole numbers plus the positive integers. And so I'm going to have the square root of 9 and 0. And then the other option I'm going to have is -9. Don't put -1.3 there because it's not the opposite of a natural number. So it's not going to be an integer. All right. Now, at this point, then, all integers are rational numbers. So the 3 written as square root of 9, the 0 and the -9 go there. But then we want to look for decimal representations for rational numbers that repeat. And so what I see is I see this -1.3 and 0.3. Now these will repeat zeros after, so they repeat forever. So I know they're also going to be rational. So I'd put -1.3 and 0.3. So the only other question I have is this square root of 10. And if you type that in on a calculator, you will see that it's like 3.2. And then you'll probably, through 10 digits, you will see that those digits are not repeating. And so you suspect that that number is irrational. Now, notice how if it was natural, it's whole. If it's whole, it's an integer. If it's integer, it's rational. But irrational numbers are completely separate. These all have a repeating decimal representation, but the square root of 10 is the only one that doesn't. So it's the only one that fits in the irrational category. And then if it asks me which ones are real, I would list all the numbers, the whole list in this case. Okay? As long as it's rational or irrational, it will be real. Okay? So that's the next kind of problem that you have to deal with. Okay? Alrighty. Let's go to the next thing. Oh, and yes, you will hear me yawn on occasion while I'm doing these things. I don't know why. I've been making these videos for years, but I yawn. So I apologize. So one of the things that we like to talk about when we do number systems is we like to talk about order. And when we talk about order, what we're really talking about is what order are the numbers being placed on the number line. And so we introduce the inequality symbols to help us be able to state that. And the inequality symbols, essentially, this one here means it's to the left on the number line, or if you wish, it is less than. All right? Whereas this symbol means it's to the right on the number line, which means greater than. Okay? And this is fairly simple. I could put the numbers, say, -4 and 3 on the number line, and I could say, oh, -4 is to the left of 3, so -4 is less than 3. Okay? So if you put the numbers in the right spot, you can talk about that. All right? Let's do a trickier one. How would I compare 7/4 and the square root of 2? So I had put those on the number line earlier, so let's do that. Essentially, what I had done is I had changed them to a decimal. Used a calculator for the square root of 2. And same thing, 7 divided by 4, could have used a calculator for that. And so now when I look at these on a number line, all right, I know that the square root of 2 is right around there, and 7/4 is right around there based on their decimal representations. Now, what I see is the square root of 2 is on the left, and so, but mathematically, I read this from left to right, so I'm really asking, where's the 7/4? Well, it's on the right of square root of 2, so 7/4 is greater than the square root of 2. Okay? And that's how I do that. And that's order. Finally, the last thing we want to chit-chat about is the idea of absolute value. All right? And absolute value essentially has a definition. And I'm going to give you that definition in variables. And we're going to move kind of beyond a way of thinking about it. Most of you have probably thought about absolute value as it makes it positive. It makes it positive. And that's probably how you've thought about it. And I can understand that. Most elementary teachers would say if you write the absolute value of 2, then the absolute value of 2 is just whatever the positive of 2 is, which is 2. In the same way, the absolute value of -3, since this is a -3 and the absolute value makes it positive, that means this is 3. Now, that's okay for a elementary understanding, okay? That the absolute value bars make the number positive. But we need to go a little beyond that. So I want to show you something in variables that's going to maybe blow you out of the water here a little bit, but is really important. We're going to make a definition, a mathematical definition, which I abbreviate this way. And that is that the absolute value of any quantity, okay, is equal to one of two things. Okay? It's equal to one of two things. It's going to be equal to just that quantity if that quantity is not negative or positive or 0. If I know that that quantity is positive or zero, then I rewrite the absolute, I just drop the absolute value symbols and rewrite it, okay? If, however, I know that the quantity inside the absolute value is negative, then I rewrite it as the opposite of that quantity if the quantity is negative. Now, that may seem a little bit strange, but I want to show you how it works. Suppose I said the absolute value of 2. So I ask myself, is 2 positive or negative? So I'm asking this question right here. And in this case, 2 is positive. Since it's positive, this says just drop the absolute value. You see that? Because it's already positive, I just drop the absolute value symbol. I don't need it. In the other case, if we had the absolute value of negative 3, then I ask myself, is negative 3 positive or negative? Well, it is negative. Therefore, to write the absolute value, I need to take the opposite of what's inside there. So I need to take the opposite of negative 3. But the opposite of a negative is positive. This is the slight difference in understanding when you use the definition of absolute value. Now, where's this going to pay off? Later on, when we're starting to solve equations with absolute value and inequalities with absolute value, etc., either in this class or another class, this helps me do the problems right. So in other words, I don't just follow a rule. I ask myself, what does absolute value really mean? And this is what it means. And so I use the meaning to guide me rather than just following some arbitrary rule that I feel like I have to memorize again. Okay, so this is it for 1.2, or excuse me, 1.3. You need to also watch the 1.4 video. All right, talk to you later. Bye.